Hi, in this video we're going to look at the definition of the derivative again, and we're going to use it to prove a differentiation formula. In particular, we're going to show that the derivative of sine of x is cosine of x. Let's go over the definition again. So if we have a function, we can write f prime of x equal to the limit as h goes to 0 of the difference quotient, f of x plus h minus f of x over h, provided this limit exists. Recall this gives us the slope of the tangent line at a point on a curve. It gives us the instantaneous rate of change of the function f at the point x, comma f of x. And this way of computing the derivative will work for functions. As we'll learn later, we'll have a list of differentiation formulas that make computing this limit not necessary. But this is a very important thing to know because it does allow us to prove some of those differentiation formulas and can always be used to find the derivative if you forget the formula, or perhaps we need to prove that a particular differentiation formula does indeed give us the right derivative for a function. Okay, so to tackle this particular derivative, the derivative of sine of x equals cosine of x, we're going to need some limits that we talked about earlier. These are the two that dealt with sine and cosine. This is the one that's typically talked about. The limit as x goes to 0 of sine of x over x equals 1. The way this was shown was via either a geometric argument, or we can make some clever comparisons with some other functions, one that bounds it below and one that bounds it above. Both those upper and lower functions have the same limit, and then using the squeeze theorem, we showed that this is 1. Using some multiplication and some trigonometric identities, we can get this particular function, cosine of x minus 1 over x, and this limit as x goes to 0 is 0. Okay, so if you are okay with these two limits, we can then find the derivative of the sine of x using the definition. So let's start. So the derivative here, we've got the derivative sine of x, and note the d dx, this is the Leibniz notation. The f prime is the Newtonian notation. There's really no difference other than this kind of acts as an operator on the function. D dx operates on sine of x. The prime here just indicates that this f prime of x is representing the derivative. Okay, using the definition, this is the limit as h goes to 0 of the difference quotient. So we'll have f of x plus h, that is sine of x plus h, minus sine of x all over h. Okay. So if we were to try to apply the limit here, h goes to 0, using direct substitution, it would not work. We would get sine of x plus 0 minus sine of x, which is 0, divided by, well, h goes to 0, h goes to 0. 0 divided by 0. All right. So we need a way to simplify this, and if you watched the previous video, you know that when we had a polynomial, we multiplied everything out, some things canceled, and we were able to get rid of that denominator of h. We'd like to do the same thing here, except you can see that sine of x plus h doesn't really lend itself to being expanded in the kind of a polynomial sense, although we can do something to this sine of x plus h. If you recall your trigonometric identities, we have sine of x plus h. We can use a sum formula to split this up. So we have the limit as h goes to 0, and sine of x plus h is going to be sine of x cosine of h plus cosine of x sine of h. So this is what sine of x plus h breaks down into using the sum formula. We subtract sine of x, everything divided by h. Okay. So this takes our sine of x plus h, splits it up. Now we have sine of x, cosine of h. We don't have this x plus h in the argument anymore. And that'll allow us to do some manipulations of this expression. Notice that we've got a minus sine of x here. And this first term has a sine of x with a cosine of h. What we're going to do is we're going to group those two together. Let me get a different color. We're going to group these two terms together, and then we'll leave this other part on its own. So we have the limit as h goes to 0, and what I'm going to do is I'm going to factor out that sine of x. And we'll be left with cosine of h minus 1. So we took the sine of x out of this term, left us with cosine of h. We took the sine of x out of sine of x, and we're left with minus 1. Okay. All that over h, and then we'll have plus, we have cosine of x times the sine of h divided by h. Okay, now I went ahead and split this up over these first two terms divided by h and this term divided by h. Now if these have a common denominator, so we could combine them and we would get exactly this expression right before. Okay, the reason I'm splitting it up like this is because I want to apply these limits, and you can see that we have two opportunities to do that here. We have cosine of h minus 1 over h. That fits this form. Limit as, we just replace the x's with h's. We'll have the limit as h goes to 0 of cosine of h minus 1 over h. It's exactly this. Sine of x is a constant with respect to h, so we can apply the limit to this, and this part right here becomes 0. We can apply the limit to this term. Cosine of x is a constant with respect to h, so this is just a constant multiple. Sine of h over h, the limit as h goes to 0, this is 1. Okay, so we have that this is the sine of x times 0 plus the cosine of x times 1. Right, well, sine of x times 0, that's just 0. Cosine of x times 1 is cosine of x. Okay, so the derivative of the sine of x is cosine of x. All right, now that we've done this, what you should do is to take the derivative of cosine of x and see what that ends up being. It'll be negative sine, but work through just like this. You'll need these two limits. It'll work out very similar to this.